Okay, well, hi. This is the alternate Electron Upgrade in a nutshell talk. Basically, I'm going to talk through the 18-page startup thread about this very long-running project with facial expressions and stories from my childhood. So I'm Philip Pearson. I've been a startup member under the name myelin for a while now. I joined right after winning an eBay auction in April 2016 for an Acorn Electron. My first piece of Acorn hardware in about 30 years, and now the start of a bit of a collection. I keep playing quite a lot at my garage now. So this project's been going since about 2015. It's involved quite a few people. It started off with a wish list, lots of dreaming, turned into a very nice FPGA design. It's now gained not one, but two, maybe three custom circuit boards, one of which is my contribution. So basically the project, it's a replacement for the ULA at the core of the Electron. It brings higher speeds, extra memory, maybe better video, and it has a whole lot of future potential once you get around to implementing it. I imagine everyone knows what an Electron is. Just to fill in any gaps, fundamentally cost-reduced version of the BBC Micro, with pretty much all the circuitry, all the digital circuitry implemented in one giant ULA chip. Much smaller because of this, but missing tons of interfacing. Biggest limitation, it has 4-bit memory. The 6502 still sees 8-bit, an 8-bit bus, but there's only 4 1-bit wide DRAM chips, and so every memory access takes 2 DRAM transactions. This means it has, at best, half the memory bandwidth of the BBC Micro. At worst, way worse, some video modes. In some video modes, the 6502 is only actually running during blanking periods. It's got simpler video. There's some scrolling limitations. I believe the start address of the start address of the screen memory is settable, but only at a fairly granular level, something like 32 or 64 bytes. So smooth scrolling doesn't work nearly as well in games. There's no mode 7. The audio is basically bit banged. It's basically a GPIO, so you can turn. It's a square wave that gets filtered a bit at the end. The tape is more or less what it is in the BBC, I think, but instead of a whole ULA just for the tape, it's just a little bit of this one. The keyboard is a little bit weird. The columns of the keyboard are wired up to the CPU's address bus, something I've never seen before. And then the rows go back to pins on the ULA. And then the disk interface is gone, Econnet's gone, no user port, no tube. The 1 megahertz bus is sort of still there, but not quite in its same form. Instead, there's a PCB edge connector out the back of the machine that brings out all of the 6502's bus, plus a few other internal signals, power, sound, etc. And so, everything's up to the peripheral designer. So as such, we ended up with a whole lot of peripherals that plug into the back of the Electron. First is Acorns +1. This picture's from RetroKit. This brought the ROM interface and the 1 megahertz bus out into a more convenient cartridge port, which is kind of interesting because now you've got all these things which really just plug straight into the top of the machine, makes things very accessible. Plug in game cartridges, and then there's a lot of third-party things, many designs from Dave Hitchens, all sorts of others. This photo is from Chris Acorns, and this is roughly the machine that I had when I was 5 years old. My first home computer was an Electron. I was 5 at the time, growing up in New Zealand. My parents bought it. It was about somewhere between 4 and 6 years before we got our next computer, which was a 286, I believe. So the Electron accumulated lots of expansions over the years. First a +1 dot matrix printer, then a +3. I think at some point it gained some sideways RAM, had the +3 modified a bit too, because I've got some DFS formatted 3.5-inch floppies, which I believe are a bit of a rarity. I have kind of childhood memories of unscrewing the case. When it started getting really crashy, I would unscrew the case and I would pop the ULA out and kind of blow the dust off or whatever I thought I was doing at that age, and popping it back in and crossing my fingers. I'm pretty sure I thought it was the CPU, but yeah. So that was over 30 years ago now. So I got that Electron off eBay a couple of years back, and I've been designing a series of ever more complicated add-ons since. So this brings us, to the UEU. It's kind of the concept is kind of a holy grail expansion that brings back everything that's missing from the B, and adds in kind of the kind of kitchen sink of whatever everyone wanted. So the start thread of this begins at the start of 2015. Dave Hitchens, David B, and Paul B drinking in Oslo, dreaming of a ULA replacement that would turn the Elk into this all-singing, all-dancing power machine. The idea, desolder the ULA, fit a socket, and have an FPGA in there, have a physical switch to select between normal mode, just a bog standard Electron, enhanced mode, which is still an Electron. It still feels like an Electron, but it has fast memory, better sound, all that sort of stuff, and then another setting for full B emulation. And then later on in the thread, people came up with sideways RAM, improving video, all that sort of stuff. So much discussion about all this. It culminated in Hoglet making the Electron FPGA project in late 2015, which implemented the entire ULA and VHDL, and also the rest of an Electron emulator to test it with. So here it is running on a Papilio Duo and with the classic computing shield. Oops, where am I? Yeah. In mid-2016, Dave Hitchens then desoldered the ULA from an Electron, fitted a socket, made a PCB that plugged in there and broke out all the signals. So later that year, Hoglet got an Electron working using this board and his code running on the Papilio, and amazingly it worked. Lots and lots of flying leads. I can only imagine what the signals actually look like here, but it worked. Here's a picture of a screen. So that was really cool. So we're up to, I believe, late 2016 at this point. So this is 2 years before I even had an Electron game. So sometime later, I've been following the UEU thread and considering if it was possible for a while. It's fairly straightforward, bit of work, but nothing, no surprises. Make a board with an FPGA and some buffers. But making one that could really improve on the Electron's capabilities and still close didn't seem practical. So I wasn't even aiming to take either of these projects at this point. I just wanted to do something interesting with an Electron, and I really wanted to have an internal expansion. Replacing the ULA felt like too much work. I wasn't confident enough that I'd be able to do it. I really wanted to do an internal expansion. So the CPU socket at 1 volts, because there aren't really any 5-volt FPGAs that are still active and available these days. So I made this adapter, desoldered the CPU. Electron. With that, it came out okay. And that I figured I would plug into the top. But yeah, this is kind of a keeping your options open type thing. So here it is with FPGA dev board. It's a Spartan 6 FPGA and a Raspberry Pi. So yeah, still didn't know what I wanted to do, but I'd shown that you could stick an FPGA into an Electron, still have it work. Also that the tube worked. Not really any software liked it very much, but it worked. So time went by. I happened to decide I wanted to experiment with BGA chips. basically all the interesting looking chips seem to be in VGA. A horrible format for hobbyists, but I figured if I could get it working, it would open up a lot of possibilities. Also, 4-layer boards are really expensive to make, so I tried to get it to work on a 2-layer board. I figured that if I could get it to work on a 2-layer board, then it's practical to make tiny 4-layer boards, but it's also quite practical to make quite large 2-layer boards. They're pretty affordable. So if I could get the VGA chip working on a 2-layer board, then I could have a fairly retro-looking board just with this one VGA chip right in the middle, and that, yeah, opened up lots of potential. So surprisingly, this actually worked. I've had many people tell me just big VGA chips like this. This is a 0.8 millimeter pitch, 169 pin VGA. But it did actually work on this little dev board here. I couldn't get all the pins out, but I got enough of them. The first time I tried soldering it, I made a complete hash of it. I didn't have a stencil. I didn't have any solder paste, so I just kind of tried to get some solder on all of the pads, and I reflowed it on top. About half of the pins seemed to work. I could program it with JTAG, but when I tried to actually do something useful with it, I found many of the pins had just not connected or something. But I made a second one with a stencil, and it worked beautifully. Here it is inside an Electron on that board in the earlier slide. It's that thing right in the center with all of the wires attached to it. It's the BGA board wasn't actually big enough to cover all of the pins on my adapter, so there's a bunch of flying leads to connect to them. But yeah, amazingly, this one worked. It implements a bit of sideways RAM. There were all sorts of things I could have done with it, but I just kind of ran out of enthusiasm after doing the sideways RAM. I was like, it was obvious I would never be able to close the case with this thing, but I'd proven that I could use a BGA, so that was cool. Sometime later, I ended up making, I think I've got one here. This thing's called ArcFlash. It is a ROM emulator for the 4-ROM Archimedes machines. It's got a CPLD and some flash on it, 16 megabytes of flash, so it can pick between operating systems. So the CPLD here, it's another 0.8 millimeter BGA, and the flash chips are 1.0 millimeter pitch BGAs. And this one worked. So I was sure that this wouldn't solder right, but it did. It worked just fine. So this gave me a bit more confidence. Now, 6+ months later, I think the consensus on the Ultimate Electron Upgrade thread was that it would never happen. It was too much work, and it would be really unreliable. A new member showed up in early 2019 who was very, very enthusiastic about the project and wouldn't drop it, even though we were all very discouraging about it. He kept being enthusiastic to the point that I started getting enthusiastic about it too. So I was like, whatever, let's try making a circuit board for it. Maybe it'll only work for me, but it's worth a try. It probably won't be that hard compared to this last thing that I've just done. In hindsight, actually, it turned out to be several times harder than the last thing. It's by far the most difficult board I've ever designed. So started out with the ULA footprint, and it's based on the board from Dave Hitchens, his breakout. Figured out the pinout and everything. So it's the same size as that. I believe it's the biggest board that you could fit into the Electron without covering the RAM chips, and without interfering with a master RAM board. So I started with the ULA footprint, added the FPGA, basically copied and pasted from my other project, the flash chip from ArcFlash. I spent ages trying to figure out how to fit a VGA output in there for video NULA support. Just couldn't figure it out. There was no way you'd be able to have a VGA cable coming out of the Electron's case. It would have to be, some flat cable or something. I didn't want to drill holes in the case anyway, so I went back and forth on this for a while, and then eventually just punted on it and said, okay, let's just make it RGB only. Added SDRAM, which is the other BGA chip to the right of the FPGA there. At this point, I started to get concerned about pin count. I thought 169 pins would be far more than we'd need, but actually they were disappearing quickly. Chris Morley noted that a QPI flash chip, it looks which you would imagine would be really slow. Everything is over just 6 pins, but he noted that you could get it to fetch a byte in 200 nanoseconds, which would actually be okay for an Electron. So I ditched the flash from my other board and stuck this little 8-pin thing in instead. It's been ages and ages working through all the buffers. The big problem with this board was that it was something like half the board would have been covered in buffers if I was using normal sized buffer chips. But I found these tiny little BGA buffers. They were the 74LVT 162245. I was excited about LVT. LVT seemed fast and 5-volt tolerant, and it has 22 ohm resistors on its outputs, which terminates things a little and should hopefully make the high-speed signals from the FPGA a little more palatable to the slower logic on the outside. So that's those 2 BGA chips inside the ULA socket there. What else have we got for audio? I was considering just making this a GPIO, but I thought, what the hell? We've got some room. Let's add a DAC. So I put something like a 24-bit DAC on there for our Electron's little 1-bit output. That's it in the bottom right. And then disaster struck. I'd been feeling really sick for a while and ended up getting diagnosed with type 1 diabetes and having to take a break for a month because I could barely see. Turns out when you have really, really high blood sugar and then you start going insulin and the blood sugar goes down, the sugar stays in your eyes for a really long time. It takes about a month for that to go away. So I could barely see for a month. I was despairing of not being able to solder ever again, but luckily that all went away. So that was nice. And I could get back to this project. So yeah, after a bit more work, I had something that started to look like a circuit board. I posted this picture and got some interesting comments on Stardot. People realized how terrible this one was going to be to solder at home. Here's a close-up of the FPGA and the SDRAM. So the SDRAM is the thing on the right. You can see the ULA socket down the bottom. I managed to, this was my first time, actually no, my second time working with these design rules. You can see you could fit 4 traces in between every pair of pins on the ULA, which I was sure would create horrible crosstalk, but miraculously seemed to work okay. And finally, here we go. This is the board I sent off for fabrication. So this, I did that at JLC PCB in China. I've heard some horror stories from JLC, but my 4-layer experience with them has always been good. I didn't push it as far as it could be. They claim that you can do 3.5 mil traces in spaces, but I used 5 mil. So this is still 5,000ths of an inch, which is pretty tiny. What is that? That's about 1/8 of a millimeter, I think. But yeah, this one it turned out quite well. Here's a microscope picture of the FPGA footprint. It's pretty cool. You can see so FPGA footprints are kind of weird. Whereas with normal with most chips, with TSOPs and SOICs and stuff, you have a big enough pad that you kind of don't really need to think about the geometry of the pad. You just have a big rectangular pad, solder mask around the outside, everything solders fine. With BGA, there's 2 ways to do it. They call them confusingly, they call them SMD and NSMD. SMD is solder mask defined, NSMD is non-solder mask defined. This is non-solder mask defined. You can tell it's that way because the pads are actually smaller than the solder mask openings. So you can see that's why there's a little halo around every pad here. What this enables is when the BGA sits on top of this, when it's soldered in, the FPGA will settle a little bit further. Also, it lets you use smaller pads, which is great when you're kind of running up against your design rule limits. I think if I did NSMD for this, I wouldn't have been able to fit the vias in between the pads on the FPGA. Obviously, that's an essential. There's no way I would get those signals out without that. I think people typically use more than 4 layers for this size BGA, but I was okay with some trade-offs, so this worked out well. Here's the actual board with all the surface mount components soldered. Took about 2 hours. From stenciling, you put the circuit board down on a flattest surface you can find. There's a stainless steel stencil which has been laser cut with little openings for where the solder should go. So you very carefully orient it over the top, squeeze some solder paste on and squeegee it over. Very carefully take it off, hope that you haven't made a mess of it. Place all the components with tweezers, and then you put the whole thing, ideally in a surface mount oven, but I just put it on a hot plate. There's a video somewhere else on YouTube of me reflowing something on a hot plate. It's a $20 thing I got from Amazon sometime, and it works just fine. You can. It seems to also work quite well for. It works well for the tiny components, and it works quite well for the big things that sit on top. I hear it's very good for things where they're on top of the board and they have big plastic housings which melt in a surface mount oven. They work fine on a hot plate. So it's been my assembly method of choice. Here it is with all the hand soldering done for all the through-hole components. Lots and lots and lots of pins to poke down into the ULA socket, and then a bunch to come up. There's the JTAG connector, so I can program the FPGA in the bottom right here. On the left, connectors for the debug microcontroller. And here it is in an Electron. This was not actually running yet. I just stuck it in here so that I knew that it would actually fit, and it did. So that was nice. I then took it straight out, powered it up. Some smoke came out, which was scary, but everything seemed to work okay. I had no idea what the smoke was for a little while later. It turned out I'd soldered one of the buffers the wrong way around, 180 degrees out. Luckily, it was not one of the BGAs. It was the little TSOP. It was a 748CT125 in the bottom left corner of the ULA socket. So I could desolder it, stuck another one on, and it worked. So the bring up process for a board like this, you sort of start from the outside and you go in. I got some code running on the debug microcontroller, the chip in the bottom left corner, and then the FPGA, just something simple that would pass through the SPI connection from the microcontroller to the flash. Then I could verify that the flash was responding by talking to it from the microcontroller, managed to program some stuff into it for use when I got everything else working. And then I checked all the pins one by one. I had basically a resistor connected to a wire which plugged into either power or ground, and I would touch it to each of the pins one by one, and then run a debug command through the microcontroller in the FPGA, which would read out what it thought the pins were. Everything worked. So that was a small miracle. Usually there's some subtle mistake somewhere, but I guess I'd obsessed over it enough. I'd let this circuit board design sit for quite a while I thought about it before I actually fabricated it. That seemed to pay off. So after fitting the new 748CT125, its outputs also worked, so it was time to go into an Electron. So I plugged it in, and nothing happened. No video output. I didn't have a scope at the time, I had a logic analyzer, but this the Salier unit you can see there. But no video, so I managed to blink the caps lock LED so I could tell that the FPGA was running, but caps lock is just a GPIO basically. So there were all sorts of things that could be wrong. The ULA generates the clock for the system, and I knew that it would generate a clock with extremely sharp edges, which would probably cause issues, especially once you plug the whole lot of stuff into the back. So I put a little filter on the end of the clock, filter on the output to try to smooth it out a little. I suspected maybe it was just completely removing the clock. Instead of smoothing it, it was turning it into just a little wiggle. So I desoldered the capacitor there, and then something came to life. I think I could see something using the using Hoglet's 6502 decoder at this point. But it was not making it very far into the boot process. It was reading something out of the ROM. So yay, ROM input was working, address and data bus were working fine. Clock was working, but it turned out that the ULA is supposed to pull up the NMI and the IRQ pins on the 6502, and mine wasn't. So You can't see it on here. I guess this photo was taken before I figured this bug out. There's a couple of through-hole resistors, through-hole resistors soldered on top of the now working one. So after that, I turned it on, and an Acorn Electron banner showed up, and then quickly scrolled off the screen to be replaced by lots and lots of ats. So, so it was alive. It was reading from the ROM. Something was going, but not everything. So once again, Hoglet helped figure this one out. 602 decoder was indispensable. I could take a trace of the startup process and upload it to Stardot for further analysis. Problem here was that those buffers, those 74LVTs that I was so excited about, happen to have this thing called bus hold. Now, bus hold is really cool. Fundamentally, what it is and all the CPLDs I use have this as well. It's designed to make it so that bus lines don't float. They just keep the value that's on them. It's basically a buffer with a big resistor on the end, and the input is connected to the output of the resistor, and then this is connected to the bus line. So what it does is when somebody's driving the bus, it doesn't do anything. But when nobody's driving the bus, this the buffer takes the current value on the bus and then passes it back out through this big resistor. Now the Xilinx CPLDs the XC9500s that are used in most projects on Stardot are the resistor on them is about 50K. So I expected that the LVTs would be the same. But no, the LVTs are designed for really high speed stuff, and their resistor is about 5K. So this basically overpowers everything. It's caused a problem later on, but in this case, what it did was it meant that the LDA or LDY instruction or whatever it was that the OS used to check for the existence of a ROM in an empty space was instead returning the last byte of the instruction. And so this resulted in the OS thinking that there was a language ROM in position 15 and trying to execute it. And whatever, I think the first thing it does is it reads out the title of the ROM and prints it. And so I guess this resulted in a never-ending string of ats. So here we go. So after, so I got the FPGA to instead just return FF bytes for everything in the higher ROMs, and it came to life. But the keyboard didn't. It was killed by the bus hold. How the Electron's keyboard works is like most keyboards, it's open collector. So there's some 33K pull-ups, which result in the lines reading high when no keys are pressed, and when you press a key, one of the lines goes low. Except 33K pull-up versus a 5K bus hold resulted in a very slow or non-existent high level on the pin. So some keys kind of worked, most keys read as something else. It was obvious the keyboard was sort of working, but just not very well. Here's a view of what was going on. This is basically the hack that I implemented to make the keyboard work, was to massively stretch out the clock cycle. It's out to about 3 microseconds when reading the keyboard, because it took quite a lot longer than it was supposed to rise back up to a 1 level. So this made it work. Amazingly, or amazingly, as we like to say here, it made it work, but everything was really slow. Trying to play games was terrible. Yeah, the Electron ran even slower than normal, so the ultimate Electron upgrade was a bit of a downgrade at this point. But here we are, very crisp video output, thanks to the CMOS buffers I was using. Successful if slow keyboard input, so this was very exciting. And I was pretty daunted by the buffer situation, but it turned out that there was another buffer in the same package. I thought I'd been very clever by finding this BGA package. It made it possible to make this very small board. And then I thought I'd painted myself into a corner by making it so I could only use these buffers that weren't going to work. But it turned out that normal buffers, 7.4 LVCs, were available in that BGA package. So I got a few of those and soldered up another board. Here's proof that it worked. And check it out, it's even working with an external ROM. So this was pretty cool. The UEU at this point, it's using the Electron's OS ROM. It's running with an actual 602. It's just emulating the ULA. So all the interfacing seems to be working pretty well. Not 1, but 2 Mega Games cartridges in this picture, but yeah. So the next thing to get working was the cassette port, which actually wasn't that much work. I have that implemented with I'd seen some notes from Hoglet about the difficulty of getting it working if you have the cassette input going straight into a GPIO. So I put a comparator instead, and some I had it analog coupled through it. Actually, I think it's coupled through a capacitor on the outside, and so I did some I had a biasing circuit. Everything had the output pulled to the center of the biasing circuit, and a comparator. So I compared between what was coming in and the center of the bias circuit. So all I really care about are the transitions, whether the waves above the 0 volt level or below, and it worked just fine. It feels more reliable than my old Electron in the 80s, so I'm pretty happy with that. QPI flash, I don't remember exactly, but I believe that one worked. That was easier to get working than I thought. It's a relatively complicated protocol, but I managed to drive it at, so the FPGA runs it, it's got a 96 megahertz clock, and weird stuff happens when you try to run things actually at the clock rate try to do external interfacing actually at the clock rate of the FPGA, which I'll talk about later if we've got time. But so I just did all the interfacing at half the clock rate of the FPGA. So 48 megahertz, that works just fine. I got I2S working, the audio output. This is something where it felt kind of daunting. I thought I2S was some complicated protocol that only high-end audio use, but actually it's pretty simple compared to most of the memory interfacing stuff that I was going to have to do. So yeah, next on the list, SDRAM. SDRAM is terrible. It's really complicated. Instead of compared to SRAM that usually goes into expansion projects, or DRAM, asynchronous DRAM, as you see in the Electron, BBCs. SDRAM runs at a really high speed. It's pipelined and command-based. The idea here is that the latency of SDRAM is not actually much better than memory we had in the 80s, but the clock rate is miles faster. So even though it still takes 40 nanoseconds to get a byte out, you talk to it at up to 166 megahertz for this chip. And once you've got one byte out, the next byte comes out 1 clock later. So I was talking to it at 48 megahertz at the time. So it took, I was using the code for 96 megahertz, but I was using a 48 megahertz clock. So it took, you activate a row, and then you wait 2 clocks. Then you activate a column, wait 2 clocks, and then data starts coming out. And when you're done reading data, you have to do a pre-charge command to basically write the data back into the RAM, and that takes another 2 clocks. So we're talking 6 clocks to access 1 byte, which is basically the worst possible way to access SDRAM, but it turns out that it's just fine for us. 60 nanoseconds to access a byte is actually just fine when you have 250 nanosecond clock rates. The worst bug in this was that basically the SDRAM is 16 bits wide, but I only need 8 bits of that. Trying to be efficient, I used the low bit of the address to select from the upper half or the lower half. I was writing everything correctly using the upper and lower bank strobes, but when I was reading, I would always use D0 to 7, and so every other byte would be incorrect. So I would, the Electron would start up and it would say Acorn Electron 160K, and then I would use SR load to load something in and it would crash immediately. This is stuff to maybe talk about later with SDRAM and clocking. I'm going to skip these. Here is mode 7. Well, mostly working. This is what happens when you get the clock wrong. So the FPGA I used, doesn't, so it has block RAM, but it doesn't let you initialize the block RAM. So the Spartan 6 that you're probably familiar with, you can initialize your block RAM. You can say, I need 16K of memory, and it should start out with the contents of the Electron's OS ROM. Can't do that with the Max 10, at least the compact feature version, which is the affordable one, which only requires one power supply and not three. So what I had to do was, to get the mode 7 character data, I had to write code that would read it out of the QPI flash and write it into the SDRAM. So before the Electron boots, it does this little burst of reads from the flash and writes into the SDRAM. Sorry, not into the SDRAM, the block RAM. So yeah, and also I got the clock wrong. I forget exactly, but I like how this looks. Usually if you read from screen memory wrong, you get pixels missing. But how teletext mode works is that actually it's a character mode, and so you get whole characters missing. Fixing the clock, ta-da, it looks nice now. So here we go, yeah. Working mode 7. I don't really know what to do with mode 7 on an Electron. It's used for everything in the BBC, but you know, it's not there in the Electron, so no one uses it. But it works. Here, I had a bit of a break here. We're up to August 2019 by now. So I took the unit to the Vintage Computer Festival in Mountain View, and basically nobody was interested in it because nobody there knows anything about Acorn machines. We had an A3010, and people were very excited by that because everyone's heard about ARM, but they didn't realize that ARM is the Acorn RISC machine and the origins of it. And so seeing this machine that was actually that the ARM chip was actually designed for was very exciting. But there was some familiarity with the BBC's computer literacy project, but the Electron, no one really knew about the Electron, and some guy's FPGA board for the Electron was even less interesting. So I was a bit demoralized at this point. But then I made this board pictured and sent it to Dave Hitchens, and he took it to Abug. So yay, people who knew what this was about got to see it. This one had other keyboard issues, which Dave gave the board to Hoglet, and he noticed that on keyboard reads, the ULA wasn't correctly stretching the clock at all. So you saw that earlier slide of me wildly stretching the clock to make it work. Well, it turns out we had the opposite problem here. We've just got a 250 nanosecond clock cycle instead of a microsecond, so it just wasn't working at all. It turned out this was because of some synchronization that I'd added, because we had an asynchronous address signal coming straight into a block RAM, which really felt like the sort of thing that you shouldn't do in an FPGA. So I'd put some synchronization in, but it also resulted in the ULA code getting the address a cycle too late and stretching the wrong cycle for the keyboard. Fixing that, ta-da, keyboard works well. Now the keyboard lines get up to 5 volts before the falling clock edge, and so yeah, it's reading properly. So I made another one. Here it is in my Electron. Thank you to Dave Hitchens. He gave me this Electron. And a +1 and a +3. It's everything so I could test it. So eventually I decided to go get the SDRAM working properly, figuring out all of the crazy clocking stuff you need to do to get it working at the actual rate of the FPGA. Much time learning about set input delay and set output delay for FPGA people. So yeah, this brings us to early December last year. I pretty much haven't touched this project since. Although after writing this talk, now I realize there's all sorts of interesting things that I can do with it. Most annoying thing is that those BGA buffers, which were basically the reason that I could make this board fit, have been discontinued. It turns out when you're really clever and you use chips that are hard to find and aren't documented super well, the suppliers tend to decide that no one uses them and they should ditch them. So I'm going to have to replace those with something. I'm not looking forward to that, but there will be another spin of this board. But Budgie, who may be on this call, I'm not quite sure, another poster on the Ultimate Electron Upgrade thread, has made his own his own ULA board with the same FPGA, but not an BGA package, and entirely using TSOC buffers. So without the SDRAM and things, he's going for the ULA replacement rather than kitchen sink trying to add in everything we could think of approach. But managed to make it fit, so that's exciting. I'm going to ask him if I could steal his layout for those and for the next release of this. So yeah, which means it's probably time for a demo. Here we are. It's Elite, running on a machine without a CPU. So this, at some point, I got the soft CPU. It's using the T65, the T65 6502 module, the HDL module. So the FPGA is actually emulating the CPU right now. This Electron is basically an I/O device. The analog stuff is working, but the DRAM's not being used. Oh, the ROM's. I think I'm reading out of the ROM. But the CPU is actually inside is actually on the ULA board. But it's got an SD card, so it does MMFS. All the flash works, so I dumped out the contents of my Mega Games cartridge and wrote them all into the flash. And with a couple of lines of VHDL, I have an internal Mega Games cartridge. So this machine here without a +1 thinks it has a Mega Games cartridge. So here we go. It's a little. I may need to. I found that Mega Games cartridge does not like having the MMFS ROM loaded, so there's a good chance that this will just fail. Let's start. Yes. Okay.
Maybe if you can stop sharing your screen, I'll see your visible screen better.
Sorry. Let me do that. Stop the share.
Oh, that's better.
Back to video. Great. Okay, so put some monitor cables a little. So behind me is the board that I put together for the Vintage Computer Festival. In front of me here is this Electron. Here is the upgrade. Here is the lack of CPU. And here is what happens when you have a Mega Games cartridge and MMFS loaded at the same time. I just disabled MMFS, so let's give that another try. Ta-da! There's Elite loading off the Mega Games cartridge. That's actually it's a soft Mega Games cartridge running inside the UEU. I've also implemented a serial port through the it uses the debug microcontroller. So I'm running Tom Stebbins' BeadLink on the on my. Oh wow! I just saw the chat. Haha. I'll go back and read that in a minute. So yeah, so this has got BeadLink, so I can there is Repton 3 loading over a USB connection to my laptop using BeadLink. It's not super fast right now. I'm running BeadLink in full debug mode, but it works. Also, yeah, MMFS using the, I believe that it's not the bit-banged Electron version. I think it's it's whatever Hoglet put into the Electron FPGA code. I think it's the shift register version. So let's see if we can get that to work, or if I actually. Yep, there we go. So here we are loading off the SD card. So we've got some choices for filing systems here. I don't want to pull this all apart and plug a +3 into it, but I'm pretty sure that works as well. I'm going to cautiously attempt that later, I think. So yeah, so some future future possibilities for this. I mean, obviously I need to fix that buffer situation, make a new board which doesn't have the bugs. I really want to put some tests into this. At work, all the code that I work on is obsessively tested. I can make a change in a fairly haphazard kind of a way and run the tests, and it will tell me what I've broken and if I've broken code belonging to another team, all that sort of stuff. Whereas here, I changed some VHDL and I crossed my fingers. Now, in the open source world, there's a ton of verification work that's been done by the Verilog community. And there's also some things being done by the VHDL community, but as far as I can tell, I don't believe that there is an open source project which will run verification on mixed Verilog VHDL designs. The vendor software seems to be very, very expensive. Intel sells a version of ModelSim for $2,000 a year, which is not what I want to be doing. I'd rather, it's an open source project. I want the tools to be free too. So I have the undesirable choice of either porting everything to Verilog or trying to expand Icarus Verilog's VHDL support. I think maybe I can get away with the middle ground of simplifying some of the VHDL so it doesn't use any complicated features, and doing a little bit of hacking on Icarus Verilog's VHDL front end. It looks like it doesn't support entities right now in VHDL, which is pretty fundamental. I think basically you can have a Verilog design which pulls in self-contained VHDL modules, and Icarus will test them just fine. But you can't have a VHDL module that pulls in another module, which this project does all over the place. So yeah, let's see what I can do there. I really want some configurable bank mappings. The Electron has 16 sideways banks. 4 of them are blocked off, 2 map to the keyboard, 2 map to the basic ROM, but the rest of them you can do whatever you like. And so right now I think I've got 2 of them mapped to the Mega Games cartridge. 2 of them are sideways from, maybe 4 of them are sideways from. I think 2 are mapped to the Mega Games cartridge. 2 are left open for a +1. 4 sideways RAM, and then you've got the keyboard and the basic ROM, and then the top 4 I think are fixed. There's MMFS, B-Link, and a couple of others. The +1 ROM, the retro hardware +1 ROM. So being able to configure them at runtime would be amazing. I'd really like to be able to say, I want this bank to be RAM right now. Have the machine start up as a standard Electron, but with a modified operating system ROM or something replacing the basic ROM, so it would start up, load a menu, and let you do stuff. And it could do things like detect if there's a +3 connected, detect if you already had sideways RAM, so it shouldn't trample that. I'm pretty sure I can do an internal tube processor. The block RAM inside the FPGA is kind of limited. I think there's something like 42K, and obviously I'm using 32 for the processor's memory. There's some for mode 7, there's something for the video. So there's not a lot left. But we have this SD RAM, and like I said, you can access it in 60 nanoseconds, which means up to, I think, 16 megahertz. I think it's up to about 16 megahertz access, so I can run several 6502s at full speed. So I'm going to try that. There's all sorts of other things, like if you want to do ridiculous things like have several processors in it, to the point where, but you want to make it kind of fast, you can either do some sort of caching, or 6502 accesses the 0 page and the stack page quite a lot. So if you put those in block RAM and everything else in SD RAM, it could run quite fast. Video Nuller support would be amazing, but I don't have the pins for it. I can either try to steal pins from something else, or do something like fast serial output over the RGB lines, or out that USB port, or something like that. Theoretically, I should be able to do like 200 megahertz serial output, differential serial output on this thing, although I have no idea. I have to play. And obviously there's so much audio potential. We should be able to do full, 24-bit audio through that DAC. I mean, it depends. I've never done a mixed signal design with both digital and analog parts where the analog stuff had to actually be low noise. So I wouldn't be surprised if this is a very noisy DAC output. The signals that come into it are quite fast. They're, I think there's something like 16 megahertz signal coming into the stack. And so separating that from the analog side probably requires things that I didn't do. Yeah, that's all I can think of right now. So yeah, thank you. I think I went over time a bit, but I've got time and time for questions. So
I'm still reeling.
Cool, Bill. So this is actually the first time, I think it's the first time I've seen Dave Hitchens and Dave Banks' faces. This has all been over, or discussions have been over email and forum threads. So it's I'd hope to be able to get out to England for one of the Abugs or RISC-OS meetups or something one day. But so the pandemic has actually been quite helpful in this regard, forcing everyone to go online. So I get to join in.
What's done in Verilog?
I think I did the Flash driver in Verilog. Basically, the things which I did entirely by myself are Verilog. I prefer to use Verilog these days because of the testing.
Yeah, I do as well now.
Yeah, so maybe porting the whole thing into Verilog might not be a terrible idea.
There is a simulator called GHDL, which is quite a good Verilog VHDL simulator, but it doesn't do mixed signal.
Yeah, it's that mixed mode stuff that's the problem.
So yeah. I've ported all of BeebFPGA to Verilog so that I could run it on the Ice Storm stuff. And once you get into the swing of it, it actually doesn't take that long. There's a VHDL to Verilog translator that gets you about 70% of the way there. So it's probably a day's work to convert Electron FPGA to Verilog.
Oh, all right then. This isn't as terrible as I thought. And then we'll be able to have some really nice tests. Test the whole system with I'm pretty sure I found a Verilog test, a test version of the SDRAM chip, which is ridiculous. It's so funny seeing SDRAM implemented using that sort of test only, the non-synthesizable Verilog. It's like for people who aren't familiar with this, Verilog and VHDL, when you're, they're these languages with an enormous number of features, most of which you can't use when you're trying to design stuff that works on actual hardware. But if you're just doing it for simulation and testing, all of them are quite useful. You can do things like set this signal to 1, and then delay 2 nanoseconds, and then set it to 0. Of course, hardware doesn't work that way. Hardware is like, well, it's flip-flops. Stuff changes when the clock happens or sometime around it. But in simulation, you can do whatever you like. And so I've seen that, I think the flash chip and the SDRAM chip implemented like that in sort of the test only. Yes, there is no eBay shop. I'm actually reading the notes now. PyTube Direct for Elk. Yes, I've done that. That's actually I've got a cartridge that lets you connect to Pi running PyTube Direct.
Yeah, that's fairly mainstream now. I mean, Dave Hitchens did his advanced tube interface that you can just plug a PyTube Direct into.
Yes.
There's the minor issue of things like the Z80 coprocessor injects Beeb specific code back into the host. So you actually have to patch the coprocessor to get it to work on the Electron.
Yeah, I can imagine. I mean, that's sort of the problem with...
It uploads 6502 code that pokes back to the tube register. So if the tube register has moved, it doesn't work.
Oh, yeah.
And the x86 one is even worse. I've not got that working.
I'm not surprised. Yeah, so that's kind of the problem with trying to run anything designed for the Beeb or features like the tube where they weren't expected to run anywhere else. Like, yeah, registers all in the different places on the Electron. I mean, so something I haven't tried at all with the UEU is the Beeb mode, running Beeb FPGA on it. Which probably wouldn't be that hard. I think I need to do a translation layer for the keyboard because the Electron's keyboard is nothing like the Beeb's one. But I think that'd be fairly straightforward to implement. Kieran's asking how far did I get with the enhanced features? Well, I basically described everything that I managed to get working. So none of those future things. Let's go right. I'm going to go right back to the start. What was it that we wanted to do for this? Okay, so fast RAM, yes. Fast RAM works. I believe there's a 4 megahertz mode, although it crashes here because the OS ROM can't handle it. But yeah, none of the enhanced audio and video or anything.
So, big question, when do we go into production?
Whew, yeah, well, so I have my competing priorities. It's like basically these two boards. So I designed this one here, which is the ROM switcher for the Archimedes, the A3000. I think I was on parental leave right after my daughter was born, and at the end of and I was like, I will finish this board and I will get them out to people before I go back to work. Of course I didn't.
Does that mean to say you weren't changing nappies in that time?
I was changing a lot of nappies, but also 1-month-old babies sleep a lot, so it was actually a quite relaxing time. I mean, I got woken up a lot in the middle of the night, but daytimes were quite relaxing. It's like when my daughter was sleeping, my wife was sleeping, I'd be out here working on circuit designs. So I really wanted to get this one working, but I'm always a bit concerned about reliability. I really don't want to be responsible for frying someone's irreplaceable A540 or something. So I keep working on this machine. I keep working on this one and feeling kind of guilty for not getting it out to people. And the UEU happened, and I put that all on hold. And then I kind of felt that I would get back to ArcFlash and finish that. And then I don't know, I ran out of enthusiasm for that and started fixing some machines for a while. Now here we are back on the UEU. So before we could go into production for this, I was like, I feel like I'm actually pretty happy with the reliability for this, and I'm pretty sure it's not going to destroy anyone's hardware. I have to do a bit more testing with a +3, but there's less weird stuff that goes on inside an Electron compared to an Archimedes. So I think this is actually wildly more complicated than ArcFlash. I think it's a bit safer. I need to fix those buffers. I need to fix the bugs. I mean, I would not be confident making a ton of them and selling them off to people, but making a small number of them and getting people to do some testing, then there's some potential.
Next
Yeah,
week, then.
so for the Black Blob ULA owners, yes, that's hard. So one of the big catches with this project is that to install it on your machine, you either need to desolder your ULA or send your Electron to Dave and get him to desolder your ULA. I think the Black Blob ULAs, is that chip actually on the board, or is it on its own little board with pins which is soldered into the
No, it's just a plug-in board, so you just desolder it as you would the socket, and it just pops out.
There you go. So, so Kelvin, you're still okay. Just more risk of destroying your genuine ULA on its way out. Yeah, I really like the form factor of the Electron too. I do feel it's. I really want to have my Electron with its closable case. Not right now because of all the debug connectors connected up to this thing, but being able to close the Electron's case and have all that memory and interfacing stuff on the inside, this really feels like the right machine. So I wonder how many Electrons there really are. Kelvin says he has 6. I now have 3. I had 2, plus this one that Dave gave me. I'm not intending on getting any more, but you never know. I have A3000s of the machine I have the most of. I have 1 real A3000 and 3 motherboards, which Mark Hazeman from Retro Clinic sold me because he got them in a pack. Yes, nice. Someone, is that Ed with his Electron there? Approximate cost of this board, including the components and soldering stuff. I think the PCB and components, I think it's somewhere around $40 or £40. I'm not quite sure. The soldering, the assembly, that's a total wild card. I believe in quantity. I think I've heard that you should basically budget the entire cost of the components again for assembly. So if it's $30 or $40 for components, it's probably another $30 or $40 for assembly. I have no idea what the exchange rate with pounds is. I bet it's going up all over the place right now. But I think right at the start of the project, I said to expect about £100 for being able to buy one. I mean, obviously that it depends. It's like if you're trying to actually make a company and make money and pay for development costs and things, I've heard that you should be charging at least 3 times the if something costs $60 to make all up, including assembly, you should charge 3 times that. You should charge $180 for the thing, otherwise you will lose money. But I think most of us here aren't really expecting to make money on this, so we charge a bit less than that. But I think around the £100 mark wouldn't be off for like a complete assembly board. Yeah, I thought I would make a bunch of these myself for just to send out to people to debug, but I sat down with all the components one evening, stared at them for a while, and then I put them all away. It took so long. So it's just, even with all the reflow, it takes forever just to place them all.
Yeah, I think once we get a stable BOM, we can ask around, especially over see what the Chinese can do.
Yes,
if they're sourcing the components and building, I think we can probably get that down a bit. Yeah.
Yeah. Yes, I think, and they'll do small quantities as well. I think I filled out a form to ask an American manufacturer what they would do, and their estimate was something like $2,000 for 10 boards. So, whereas in China it's probably more like $10 a board. Bye, Charlie. Yeah, so I think wouldn't be unreasonable to get a few boards made. Once I think maybe once I've done the redesign with the new buffers and built up a board by hand to verify that that works, then maybe we could go. We could see about getting a Chinese manufacturer to make a run of 10 or 20 for the early adopters, people who don't mind maybe things breaking.
I'm sure there's plenty of electrons with Duff ULAs around that wouldn't
Yes,
be too great a loss, or could be fixed easily anyway with that.
that's a good point. That's something it's like I don't really see that over here in America. I have a very small window into the kind of availability of this sort of stuff. Basically, what I see on eBay, who's willing to ship to the States, and it's it costs something like £30 to ship an electron to the US, and so when I see people saying that electrons are worth £5 to £10, these are numbers that I never see over here. I paid £42 for my first one, and another 24 to ship it. And that's kind of what you expect here. So yeah, the broken ones don't make it over. So I should also say I think I mentioned Budgie's kind of parallel project earlier. He popped up on the Ultimate Electron Upgrade and Electron FPGA chats and threads a couple of months back, and has built up a board with the same form factor, but without the extra RAM and flash and interfacing and stuff. Just as a, I think it was partly as a kind of a practice, a circuit board design practice. But what he's produced is basically that ULA replacement. If you've got an electron, you want it to still be an electron. You don't care about upgrading it, but it needs a ULA replacement. I think this board would be excellent for that. You could probably you could probably do fast mode, but without like sideways RAM and stuff. So now we have two choices. It'd be interesting to see how this all goes. All right, so we're losing people, and got more questions?
Yeah, go on, Phil. Did you look at the? Hi, how are you doing? Did you look at the TI CB3T buffers?
I haven't. So there seems to be an endless supply of different kinds of buffers, and I kind of poke around every now and then and see what's showing up. But I tend to stick with the ones that I've used and have found to be reliable. And pretty much, I guess after I kind of got burned by using LVTs, I've just been designing with LVC and HCT recently. Usually I've got enough. I'm a little wary of the CB3T ones. Are those auto switching, or are they?
Yeah, they're sort of. I think they're end-to-end FET things, but I've used them, and I have to say I've not had a single problem with them, other than they won't do CMOS levels, but they do TTL levels really well. And you don't need to tell them which direction the bus is in. And I had the same problem you had a while ago with you were saying about the bus hold stuff, screwing stuff up. And I've not had anything like that with these. And I hang things off, and they seem to be so bulletproof because I'm such a klutz. And I put the 3 volt into the 5 volt and expect them to fry, and they seem to just survive. So they're probably worth a look, because some of them I think you get 24 in a package, 24 pins, and any of those pins can go in either direction. So they're well worth a look.
Yeah, that might be worth a look also for reducing pin count, getting the smallest possible package without resorting to things that Texas Instruments is about to deprecate. Yeah. I mean, I
don't know where they're going with the deprecation thing, but I think last time I looked, Farnell was stopping selling them, but you could get them direct from TI, and they said they're not end-aligning them, so they should be good for a few years. Yeah, and they are quite widely used. They're not like an esoteric thing. And go on.
Yeah, that's good. Sticking to widely used active components, I think, is what I'm going to do from now on.
Yeah, I've been stung so many times with that.
Yeah.
I can see the other thing on you were saying about the sound stuff and all the audio processing and worrying about the analog circuits and stuff. I was quite surprised when I knocked my stuff up. I didn't use a DAC at all. I just used a 1-bit, and I did PWM in VHDL, and I expected it to sound really, really crappy, and it sounds absolutely great. I'm sort of like blown away by how good it actually sounds, and I even hooked it up to a sound card and put a sine wave through it and did like a harmonic distortion thing on it, and it came out as perfect as I think I was doing 12 bits could come out, and that was my really, really basic a resistor and a capacitor filter. So if you want to look at any of that, I've got stuff that we could look at offline if you wanted.
Yeah, that's actually a really good idea. So partly this is exciting because the DAC needs a ton of passive components hanging off the side for power conditioning, and there's something like a second order filter on the output of it and stuff like that. And also it uses quite a few pins from the FPGA. If I could ditch this, then maybe this could give me a bunch more pins for the VGA output.
Yeah, and the PWM thing that I've used, I can't remember. I just picked it up somewhere on the internet and I fiddled about them myself. But it's like, I think it's like 5 or 10 lines of VHDL. It's not a lot of gates. It's a counter basically.
Yeah.
A comparator, and then output. Toggle the pin when you go past the count. It's so basic, and like I say, I expect it to be really crappy, and I've just got one resistor, one capacitor on it, because it's running at like however many megahertz. You just stick a really simple filter on it, and you're not going to be anywhere near the switching speed. So it's an easy way to go.
Yeah, I mean that's I didn't talk about this earlier, but the cassette output from the Electron is an interesting thing. It's got like four levels, so it tries to approximate a sine wave in a blocky kind of a way.
Yeah.
And I was thinking of using a couple of pins in a little resistor ladder or something to do that, and then I realized that I could just PWM it and make it as sine-like as I wanted. Turned out that feeding a square wave into a cassette recorder works just fine. But yeah, I could use PWM to make it a whole lot nicer if that turns out to be insufficient. But that's really promising that you could get away with just a single FPGA output and get good sound.
You can do a lot with FPGAs in the and analog. Back in the 90s, with a bit of trickery, with 2 resistors and a capacitor, I was able to get composite video into an FPGA, and then another 2 resistors and a capacitor to get it back out again.
That's amazing.
Wasn't the world's greatest composite video source, but it was good enough that you could get composite video across. And basically what you end up doing is in the I/O cell, you end up with a little feedback path. And so it just tries and oscillates to try and track the composite video. You don't do anything in the clock domain, but that oscillation you then feed across the FPGA, which is good at, and then you filter it back out again. And that gives you back your composite video again.
That's amazing.
So yeah, so 1-bit DACs and 1-bit ADCs are quite possible. So you can make a timed ADC if you ever need to do an ADC on the FPGA, because the inputs cells are actually pretty fast comparators at the end of the day. So if you effectively make a DAC, but you can use the DAC and the input cell to be a comparator to form yourself a little ADC, and then you can just track your signal.
That's really clever.
And again, it's only a few literally only a few lines of Verilog to do that. If you do get everything into Verilog, there's something called Verilator, which is often used for simulation.
Yeah, I think Icarus is the one I'm familiar with, but I keep seeing I might use Verilator at work, I think, for some things, the hardware people there.
Lots of people do because it's free.
It's the one that compiles
to see.
Just see.
Yeah.
Yeah, that's right. So you can actually simulate very complicated things. Yeah.
So can I ask where your day job is?
Oh, I work at Google.
It was going to be that or Apple.
Yeah. Yeah. So I don't know very much about what goes on in Google's hardware division, but I do know that it's all Verilog. So
yes. And they keep on buying people, so who knows what of the companies they buy.
That's true. There's a lot of PhD also Verilog porting on something that happens sometimes.
Yes.
So Phil, your earlier boards you made were stamped with Google, weren't they? Because obviously that's a condition of the employment.
See that? It's a little dark. So sorry, yeah, go ahead with the question.
Oh, that was it. No, will the UEU have Google stamped on the boards as well? And it sounds as if they already do.
Yes. So the condition is basically by Californian employment law, things don't belong to you unless you do them entirely on your own time with your own equipment, and they have nothing to do with what your employer's line of business. The first two conditions aren't too hard. I have plenty of my own time and my own equipment, but Google's line of business is kind of connected to pretty much everything, and so it's quite hard to do something which has absolutely nothing to do with Google. The company recognizes that, and they say, well, you're also allowed to contribute to open source projects, and you could start open source projects. Google is fine with that. So basically how it works is the copyright's held by Google, but it's released under Apache license or GPL or something. So you get all the rights that you get under those. It's just, I don't own it, so I don't get to relicense it. I don't get to do that kind of stuff. If I left the company, I would only be able to use the code that I wrote under the condition of that license. So I just release everything under the Apache 2 license, which is pretty unrestricted. Also includes patent grants, I believe. So if I accidentally infringe any Google patents, then you get a license to them for this project. It's something like that. I'm not a lawyer, but I believe there's something in there. Yes, Karen mentions you can request copyright back, but the process is a little long-winded. You basically, if you're working on a project where you can kind of make a case that Google doesn't really want to own it, doesn't have any interest in it. So I think the company quite likes having a lot of open source software copyright Google. That's good. But if you can kind of you can request to have it under your own copyright, and sometimes they'll say yes. Oh, Karen says yes. So Karen is also a Googler, and has done that for his demos, so he gets to keep the copyright. But it doesn't really bother me as long as this stuff is open source under a sufficiently permissive license. I'm happy.
Right, thanks for answering that, Bill. Have we got any more questions before we wrap up? I mean, we'll carry on. We'll stick around if people want to stay online.
Not a question, but just to say that was awesome. Thank you. That was really, really interesting, and lots of super interesting and thought-provoking things. So thanks so much for sharing.
Thank you.
But yeah, it's a great finish to the day, I think. I'm sure you've added to the numbers wanting, you want to get the hands on a UEU once they're available, and hope you find a time to get it finished, tested, and released. I don't know if there's any chance of it being ready to go into Christmas stockings this year. Is that a bit optimistic?
June could happen. I think I'm a bit ADD. I tend to I put a lot of energy into whatever it is that is the shiniest thing at the time. So as long as this one stays the shiniest thing, it's really what I think that's how my brain works.
I'm sure if it starts to wane, Dave will get you in to do another talk.
Hey, that's it. That's a good trick. So you can see when I stop posting on the UEU thread, and I guess I need some encouragement. What happened since the last talk?
Should we put you down for the August one now?
It's
been a bit of a bonanza for Electron fans today, hasn't it? We had Dave Hitchens reminiscing about press and his Electron upgrades earlier, then the 0x code and his Electron demos and the Mountain Panic conversion, and lastly we've got your talk on the UEU. It's been great.
Thank you.
I think the Archimedes need to be shown a bit of love next, so I think that's what we're looking at doing at the next subsequent events, is trying to factor a few ARC talks in.
Well,
that'd be good. Yeah.
If you give me a couple of weeks, but I could probably do an interesting talk about this little guy, and maybe the A5000 I poured dozens of hours into, attempted to restore, and stopped after frying that particular board.
But no, if we can see a virtual round of applause for Phil, and we'll I'll stop the recording now.
Woo!